Are you talking to us,
Professor,
Professor?
your mic.
Oh, I'm so sorry. Here I'm rambling on, and you guys are just sitting there blissfully ignorant as I didn't realize it was muted. I sorry about that. Okay, so let me repeat what I said in 30 seconds or less. Um, what I want to do today is just first go over any questions you guys might have about the homework or anything, and then talk a little bit about chapter 2. I have a couple examples I'd like to go through just to make sure that we're understanding chapter 2 and everything we need to understand before we move to chapter 3, and then introduce chapter 3 and the kind of the highlights of it. So that's my plan. And what I was saying is this is a little more fluid than what we would have in a typical lecture, since everything you need is on the pre-recorded lectures. So before I jump in, yes, so whoever asked me, do you mind if I share a group link? That's absolutely okay. Yeah, so that's fine. What I was going to say too is if you'd rather, if you prefer not to ask questions out loud, you can send me a note if you have a question you want me to cover and you prefer not to talk. But I encourage you, don't be shy. We're all covering the same thing here. So before I jump in, are there any questions on anything? Have you guys about anything you've covered in the first week?
I remember reading it a while ago, but what are the expectations for turning in the homework? Just I remember I think it said they have to be really neat and just very clear, right? And take the space you need.
Yeah, so the homework guidelines go over that, but just in a nutshell, you want one assignment, or I'm sorry, one problem per page. You want to make sure that it's legible, that it especially as we move forward into free body diagrams, make sure the free body diagram is accurate. You want to say what are you given, what is your find, and then when you're showing equations that you're using, show the equation with variables. Don't just start with numbers. Okay. And then when you submit it, just make sure that you use the title that I said. So it has your first initial of your first name, or initial of your first name, and then your last name, and then winter 21 homework, whatever it is. And then you'll submit that. That way, when I grade it, I have everyone's name on the assignment. Because if you just put homework 1, then I end up with 130 homework 1s, and it's harder for me to keep track of who's who. I mean, it's possible, but it just makes my life harder. So anything about the material, guys, I mean, if you don't, that's understandable, because the first week is pretty much a review. So, okay. Well, if during the next 45 minutes, something does come into your mind, feel free to interject, even if it's while I'm doing something different. So
I have a question.
Sure.
About is it all right if if there's 3 cables or something attached and one is named P? Is it all right if we assign different variables to the other ones, just like P, Q, and R?
Absolutely.
And then in our work,
Yeah.
Is that all right? Okay.
Yeah, absolutely. Yes. And remember, when you have cables that go over a pulley, that you can cut the cable anywhere, and the force is going to be the same. So on a couple of the problems you have, the cable goes up to the left and it goes over a pulley, but you don't have to worry about the pulley. You can just cut it as it's going up to the left at whatever angle it's going at, and then just treat it as a vector from that point, as opposed to worrying about it going around the cable, or I'm sorry, around the pulley, because we're not dealing with friction or the inertia of a pulley at this point. Okay, so let me just go ahead and share screen. So review chapter 2, introduce chapter 3. As I said, that's my objective. So chapter 2 summary. So what your takeaway from chapter 2 this week is being able to add vectors. As you know, vectors have magnitude and direction. And this is, again, should be all review for you guys. You're going to either add them tip to tail in parallelogram method. And I don't have you guys actually do that in class, because in order to do that accurately, you need to have graph paper. You need to assign the value of say 1 Newton equals 1 centimeter or whatever. And so you can do that, but it's very time consuming, cumbersome. It's better for something in a grade school learning what vectors are. So instead, you're going to either add them using a triangle method where you only have 2 vectors, or if you're a brave soul, you could do the polygon, though I don't encourage it. Once you get past a triangle, I would say just add your vectors by components. So just add up the i's, the j's, and the k's respectively. And then the end of the chapter, you talked about 3D vectors. So that was identifying the horizontal projection and identifying forces and converting to vector format. So that end part is important because really chapter 2 in and of itself is it's going to provide you with the tools to do stuff later, but it's not that interesting, meaning that all you're really learning is how to manipulate vectors in chapter 2. And so I'll assume after we go on to future chapters that the stuff in this chapter you'll understand, and I will just take it for granted. So please ask questions if you need to. So one of the things I've had classes struggle with in the past is this idea of projection in 3D. So for example, this example here, we have a tower and we have a 700-pound force and a 600-pound force, and that's the scalar value. And it's between cable AB and AC respectively. And then there's this cable AD, which we can ignore for the moment. And so the question in this one is, how do you determine the resultant? If I wanted to add AB and AC together, what would I do? So in this problem, we have to actually convert each one to IJK and then add them together. So of course that's easy, but they're not really in IJK now. So how do we do that? So for some of you, this might be review, but again, I think it's worth going through. So what I'm going to do is I'm going to go to my document camera and let's work through this problem. And so if you, can everyone see it okay? Is it in focus? Does it look all right? I know the document camera is okay. It's not the best. But so there's what we have. So just speak up if you can't see something. So I have FAC I've drawn 600. I have FAB going down to here. So respectively 18 feet, 12 feet. This goes out 12 feet. This distance we don't know, but we do know that this angle here is 30 degrees. So what we want to do is we want to go ahead and figure out which one each one is. So I'm going to start with AB. So I'm going to say I know that the force AB vector is going to be the scalar AB times the unit vector AB. And so in order to figure that out, I need to first figure out what each of those the unit vector components are. So one of the things is we know that this up here is going to form some angle with respect to the z-axis. So you may recall from the lecture that you saw that if we draw these values generically, we know that this force up here, force Z, is just going to be equal to whatever the scalar is, so in this case 700, and then it's going to be times cosine of whatever that angle is. We'll call theta. And it's negative because it's going in the negative direction. All right. So we can find that, but we need to find what that angle is. So the first thing we do is we can figure that out. Now, if we draw this vector as a triangle, what we end up with is something that looks like this. All right. And so this is 36. And this line on the bottom represents this line here, which I'll draw in pen. It didn't come out very good. Sorry. There we go. So this triangle here represents that. So the question is, what is this side? Well, we can figure it out because we know that's 18 and that's 12, right? So we know that this line here has to be the square root of 18 squared plus 12 squared. And so if I find that out, that's 21.63. So 21.63. So that's that side. So we know this distance here is 21.63. So now what we can do is we can calculate what this angle is. Now you can always use ratios, that's easier, but I'm gonna just convert to angles even though we're gonna convert back again to ratios. So if we do that, we end up, we take theta equals the inverse tangent of opposite 21.63 over 36, and we get theta equal to about 31 degrees. Okay, so now that we know that, because we had, this is our governing equation, we can say, we just really what we want to is we want to know FAB, we know is going to be equal to FXI plus FYJ plus FZK. So we know that FZ in this case, the component for FZ, is just going to be minus 700 cosine 31 degrees. And so that gives me negative 600 pounds. All right. So the next step then is to find what the X and the Y are. And that's why this projection idea, what you're doing is you're taking this vector and you're seeing what part of it is projected onto this XY plane. So we can find that magnitude of that force because, again, the magnitude of the force and the ratio of the triangle are the same. So we know that this line here, and what I'll do is I'll just redraw it. This is just drawing this corner here down here. We have this. So we know that this projection of the force is going to be, which we call a lot in the book, it's referred to as F sub H. We know that, and that's this up here, FH. And if I go off screen, please let me know because I'm looking at two different places right now. But if I look at FH, then I know that FH is just going to be 700, and that's going to be times the sine of 31 degrees. So that gives me a value of 361 pounds. Now, when you're doing these problems, it's fine to round intermittent. I mean, if you want to carry it through to the end, that's okay. But as long as, when I grade, as long as the answer is within a few, I'm fine. I'm not a stickler for that stuff, especially because the values, the forces that we give you, we don't know any better than a few percent. So again, feel free to round during it if it makes your life easier. So 361 pounds. So that's what, so now that we know that, then really we know that this is just then a triangle, right? So this is my, in this case, this would be my right triangle. So here's my hypotenuse. This side now becomes my component of the X force, and this becomes a component of my Y force. And so in that case, I know that F, the X, so the X component of that is just going to be FH times the cosine of this angle, which we'll call phi, and Fy is going to be equal to negative FH, because it's going the negative Y direction, and that'll be a sine of phi. So if we go ahead and plug in our numbers, if we plug in FH here and phi, and again, we can find phi very easily because we know if we come back up here, we know this hypotenuse, and we know one of these sides. So it turns out that this little angle here, phi, is 33.7 degrees. Okay. So I'll pause for a second. Any questions on what I've done? I know I'm kind of going through this a little quick. Any questions on any of the material? Does it make sense? All right. I'll take your the profound silences. Yes, sounds good. All right, so go ahead and we'll figure out what we have then. So if we go ahead and do the math for that and plug in FH respectively for these, we end up with FA, the X value being equal to 300 and the Y value equal to negative 200. Okay. So what that really says, and so I've kind of a little sloppy, but what we end up with is our FAB, then our final vector, is just simply equal to 300I minus 200J plus, I'm sorry, minus 600K. And there we have it. So the main takeaway is that we were able to project this down here, and we were able to convert just a line with one distance and no angles to its ijk components. Now, in of itself, again, it's not that exciting, but the point is that you're going to need to do this when we get to chapter 3 and beyond. So if we wanted to do the same thing for AC, we would, and you could see that if in that context, what we would do is just simply take another line, draw it down there. We could find this side of it. We could find that side of it. Since we know this is 36 feet, we know this is 12. And since we know that's 12, we can use, we can basically take cosine divided to find, we could take 12 divided by the cosine of 30 degrees, and that will give us the length of this hypotenuse, which turns out to be 13.856. And we can find the length of this, which ends up being roughly 6.928. So it's just geometry. And so once you have those values, you can go ahead and do the same thing here. You can find this angle theta up here, and you can calculate it. And so it turns out that if we were to look at it, I'll just show you what I did. We have theta up here, we have 36, we know it's 6.928, and this is our triangle again, where that's theta. And so it turns out to be an angle of roughly 21 degrees. And then we can go ahead and do the same thing. So we know that the scalar value, this is 600 pounds. And then we know that what that angle is. So we can then calculate FAC sub Z, so the force in ACZ, as essentially negative 560 pounds. We know that our horizontal projection is just 600 times the sine, so that side of the triangle, and that gives us 215.5. And then we can find our respective y and x just using this triangle on the ground. So respective cosine sine of 30 times FH. So we end up finally with FAC, and that's the value 107.8 plus 186.6 minus 560. So in terms of sig figs, remember that if the number leads with a 1, you have 4 sig figs. If the number leads with a 2 through a 9, you have 3 sig figs. And that's the rule we're going to use. So add FAC to FAB, and we get our final. And that's it. All right. So I kind of went a little quicker on the end there, but this hopefully this is something that everyone understands now. Any questions? All right. Okay, let's do something a little more.
I have a quick question.
Oh, sure, absolutely.
It seems R is usually just the resultant of the two forces. Is that true in general for this course?
Yeah, I could have just written this as R. That's correct.
Okay, cool. Thanks. Also, on the last homework problem, it looks like they're pulling him towards the shark, and that's a little sketchy, I think.
Oh, on that one? Yeah. Well, I think on that last one, I put the picture of the megalodon in there. So I think in the original problem they didn't have the shark in there, so I added that.
Oh, okay.
Yeah. The original didn't have that. It was too boring otherwise. Got to have something.
I know, that's a really nice picture. You must have been in a lot of danger to get that.
Yeah, took it live. That's right. All right. Any other questions on this? So what I want to do is let me share my screen again. I want to show you the next example. Okay, now this one is the two ideas at the end of the chapter that have had issues were the 3D equilibrium and the idea of the 3D projections and the 3D equilibrium. So this is a 3D equilibrium. Now, in this problem, and I'm not sure why. Oh yeah, there we go. So determine the maximum weight of the crate so that no rope exceeds 450 pounds. So you have this rope here from A to C, you have a rope here from A to B, and you have the rope here from A to D. So it gives you the respective coordinates of C and B, which are that, and it tells you that, and sorry, that other part disappeared, but so you want to know how big a crate you can lift without exceeding 450 in any rope, because you're going to assume the rope will break and that wouldn't be good. So we have to essentially look at this as what are the forces in all the different directions. And then by process of elimination and substitution, figure out which ones hold the most, and then use that as kind of our upper value and then calculate the weight. So how do we do this problem? All right, so here's what we have. I've redrawn it so you guys can all see it good. Okay, so what do we have? What I did instead is I've drawn the actual location. So I know that I have this force AB, I have AC, and I have AD all going out these way. And so B is at -212, C is at -2, -2, and then D is at 300. So first off, we want to figure out what are the distances. So we know that the distance AB is just going to be equal to the point B minus point A and perspective. But since A is 0, 0, 0, it makes it a little easier. So what I'm going to do is first, we know that in order to figure this out, we know that the sum of all the forces is equal to 0, obviously. And then we know that that means that the vector FBA plus FCA plus FDA plus the weight all have to be 0. All right. So we know that FBA as a vector, of course, equals its scalar value. And I write the scalar value as kind of as a slant, and that's the difference between scalar and a scalar and vector. So then we have lambda VA. So just like before, we know that our force is equal to the scalar times its unit vector. So what is our unit vector for lambda VA? Well, we know that lambda VA, if we look at the distance from B to A, we know it's going to be -2, right? And -2. Now let me write this and I'll explain. Plus 1/3 J plus 2/3 K. Now, so what I did in order to get this unit vector is I said -2, 1, 2, and then I divided that by its magnitude. So we know that 4 plus 4 plus 1 is 9, square root is 3. So this is how, this is something you'll want to, being able to convert to unit vectors. So you understand that a unit vector is just the distance. It's just the, where the magnitude of the vector is equal to 1. So I should really put the hats on top. There we go. So now we have that. We'll do the same thing. So we know FCA is equal to, and for the sake of time, I'm just going to write this in. FCA, that's going to be equal to -2/3 I minus 2/3 J plus 1/3 K. And then lambda dA, that one's just equal to 1 I, or just I. And again, these are hats, sorry. Okay, so we have that. So what we want to think about is, what are our force vectors? Well, our force vectors are just going to be with the respective values in front of them. So we can rewrite then FBA as -2/3 FBA plus 1/3 FBA IJ plus 2/3 FBA K. And we do the same thing for FCA and FD. So write that down real quick. So -2/3 FCA minus 2/3 FCA and plus 1/3 FCA K. And then FD is just FDA I. So what we want to do, and the way we solve this, is we want to then isolate our variables based on IJK. So if we look at our I variable, we know that we have -2/3 FBA minus 2/3 FCA plus FDA all equals 0. Or we can say FDA equals 2/3 FBA plus FCA. So we'll come back to this. So this is our first equation. So that's equation number 1. Then I'm going to go with the J's, and if I do that, then I find that I have 1/3 of FBA minus 2/3 FCA equals 0. So all I did was take these two and add them together. So if I solve for that, what do I get? I get FBA equals 2 of FCA. Okay. Oh wait, I'm sorry, these aren't vectors. Sorry about that. Yeah, these are all scalars now because we've divided them up by their. So we have FBA, FCA, we have FDA 2/3 equals 2/3 FBA plus FCA, sorry, it's getting a little messy. So this is my second equation, all right? So if you've written nothing else, write this down, right? FDA equals 2/3 FBA plus FCA, and write FBA equals 2 FCA. That's the important thing you need. So try to keep that on the screen as best I can. So the K, the last one, says that if we, for the K values, it's 2/3 of FBA plus 1/3 FCA. That all equals W. And all I did was that would have been this plus this minus W equals 0. I just moved the W over. So that's our equation 3. So how do we solve this? So what we do is we actually look at, we can kind of see a few things here. For one is if we go back to our equation, and I'll just go ahead and write equation 1 here again. FDA equals 2/3 FBA plus FCA. And because I know that FBA equals 2FCA, then I can substitute that in. So I know that FDA equals 2/3, and then I can substitute in 2FCA plus FCA. So all I'm really doing is I'm just substituting. And then that just says that FDA is equal to 2 times FCA. So, but we also know that FBA also equals. So equation 2, so we call this, if we have this equation, but we also know that with equation 2 that FBA equal to FCA, right? So therefore, we know that FDA equals FBA. All right. So, which equals to FCA. All right. So now what are we going to do with this? All right. So any questions up to that point? I know that it's like a lot of BA, CA, DAs, but I think if you just again, and the good thing is that no matter what problem you have, and even when we get to later chapters, you approach them all the same. You start off your diagram and you go ahead and you find your unit vectors, then you isolate them by their IJK components, and then you substitute in what you know and don't know and then solve. So that's that same process, just sometimes it's a little more tedious than others.
What happened to the 2/3 in front of the FCA on I?
On I,
Yeah. Like when you moved it over, shouldn't there be a 2/3 in front of the, oh wait, no, go down.
on this, are you talking about this one?
Yeah, right there.
Yeah, I just wrote it in, I apologize.
Oh, okay.
Yeah, you're right. Good catch. Thank you. I was getting ahead of myself. So yeah, that does have 2/3 there. So because it reappeared again when I, that's equation 1. Yeah, and it does reappear again. So we use that here. Oh yeah, that should have been in there too. Yeah. And that's 2/3. And if you see, then what you end up with is 4/3 FCA plus 2/3 FCA gives you 6/3 FCA. That's 2 FCA. So yeah, I left the 2/3 out, but this is correct. That's what should be. Thanks for catching that. So now what we want to do is this is we want to solve for W. So that's this equation 3. All right. So we know that that 450 is the highest load. We know that FCA is going to carry half of that. So we know that DA and BA are going to carry the max they can carry is 450. So we know that's going to have to be 450 is DA, 450 BA, and CA, the maximum it's going to carry is 225. Does that make sense? Because it's half of that. So what we do is we take this the W equation, the last one we had, this equation 3, and we say 2/3 of FBA, and we put in for that because that's holding the full load 450 plus 1/3 FCA, and we know it's only half, so we put in 225 equals W. So if you go ahead and multiply out 2/3 450 plus 1/3 225, you end up with W equals 375 pounds. Okay. So those are the two types of problems. That's something like this, probably not as long, will be on the quiz. So something from chapter 2 is going to be on the quiz on Wednesday. So that's why I wanted to make sure there was no questions on this. So before I go to chapter 3, because we got about 15 minutes left, are there any questions on chapter 2 or anything I've covered? All right. That's good. Okay, so let's talk about chapter 3. Probably easiest way is just to write it out. So now chapter 3, we're talking about moments about a force. A moment of a force. And so if we imagine in 2D, and you guys have seen this in physics before, but we know that if, for example, you have a door and you apply a force to it, and that's your length. So we'll say that this is your distance, and here's your point A, and this is your force. That we know that the moment about A is just equal to force times the distance. Okay, nothing new there. We know also that if we were to draw this as D, and let's say our force was like this, that's force, then we know that the only part of the force that creates a moment about A is the perpendicular component. And so if this is the angle theta, then our equation would read the same thing, except it'd be MA equals force times sine theta times D. Okay, where this opposite side would give us our perpendicular component, and that's that. So I think that's a pretty easy concept. So, but what we're going to do is we're going to spend a lot more time in 3 dimensions. So I want to explain where that comes from. So we can, when we're finding moments about a point, we either do force times the perpendicular distance, or we can do, the moment can also be something where it's R cross F. And so the moment about any point can be the distance from the point to the force crossed with the force vector. Now let's look at this just in 2D. Let's imagine that we have something like this. Where we have and so I have this, I give you as 20 degrees, that's 10 meters. And then you have a force coming off of that. And that's going to be 75 newtons. And this angle here is 30 degrees. Okay. So I'm going to call this my point here A, and I've just added these as my axes. Okay. So we have a 10 meters going at 20 degrees. There's our force. So we want to know what the moment about A is. Okay. So, well, one way would be to just figure out what is the perpendicular force. And so if we do that, we should be able to figure that out fairly easily, because we know that looking at this, if that's 20 degrees there, we know that internal angle has to be 20 degrees, which means if we want a 75, sorry, up here, that means that our perpendicular distance is going to be, if we draw it like that, then if that's 20, that's 30, that means that has to be 40. So now we can say the moment about A is just simply equal to 75 newtons cosine 40 degrees, and that's just because of the way I oriented it. Or I could have said sine 50, same thing, but cosine 40, because that's that side of the triangle, times 10 meters. Okay, so that's one way to do it, and that's the easy way, but you're not always going to be in the situation where it's really easy to see. So another way we can calculate this, and if we multiply it through, we end up with 574.5. We'll just leave it at that. Another way we do it is we say the moment about A is equal to, now this is a vector, but it's just that in 2D, we always assume that because of the right-hand rule, that this is a around the k-axis. And the notation, of course, is that because this is going counterclockwise, it's positive. If it were going clockwise, it would be negative. So if we take this and we say R cross F, in this case, we could do it the same way. So where we would set it up is we have our R vector. So our R vector, again, is, and this is, you always want to go from the point to any point on the force. So you take the point that you're taking the moment about, which is usually well-defined and you're told, and you draw a line, any convenient line to it. So I could extend this vector infinitely and draw any line I wanted to, and it would work. But this one's already there, so I'm going to use that. So I know that if I want to go from A to this point here, and let's just call it B, then I'm going to write this as B relative to A. And that's, you'll see that in my lecture, is you write these vectors as, because it's B relative to A, meaning going from A to B, and always to the force. So that's an important emphasis on this. So if I go ahead and write that, I have 10 cosine 20 degrees, right? Because that's 10 meters. And that's my x direction. And 10 sine 20 degrees is my y direction. And I have negative 75, because it's going in the negative x direction, cosine 30. So that's my x, the force. And then I have 75 sine 30. So I do my cross product, that minus that, and I get 9.39 times 37.5 minus 3.42 times a negative 64.95. And so if you add it up, I end up with 574.5. No surprise, it's the same answer. But you can see how this method is much more useful because you don't have to visualize where this vector is. All you have to know is its ijk components of these two. And so that's why in 3D, you're not really going to be able to do it force times distance. It's just, unless you have a really good spatial recognition, you're going to have to do it this way. So that's the first part of chapter 3. It's dealing with what we call is a moment about a point. Okay. And so generically, or kind of theoretically, if we were to draw it, it looks something more like this. Never mind. If you were to just draw it out, it looks something like this. So if you have some random force in space, and the good thing with these problems is you're given force, and you're given the force and you're usually given a direction. And your objective is to then convert this force into ijk components so that you can find the moment. And let's say that this is your point origin and you have a point A here. So we draw our vector there. We call that R, A relative to O. So in order to find the moment about O, we know it's just R, A relative to O crossed with the force. Never the opposite. Never cross the force with R, A across O. Now, that's for a point. Now, we know that when you do that, you're going to get some moment in space. Okay. And this is, so this moment here I'm going to draw, this is my result, right? Because when I do R, A relative to O cross F, I get a vector. So this vector is off in space too. Now, the next step, and we're almost out of time, but the next step in chapter 3 is to talk about a moment about a line. Now, it turns out that if I have a line, any line, it doesn't matter. I can project the force onto a line. And you may remember this from your math, and I cover it in the lecture. But you know that if you want to project a moment onto a line, you basically say the lambda of the line, so whatever the unit vector is for this line, so we'll call this line OL, whatever that unit vector is, you dot product it with this moment O, and that gives you the scalar value of moment OL. So MOL, sorry, it's getting messy, but that's a scalar. So what you end up with is when you do this dot that, you end up with a scalar value, and then that just gives you either a positive or negative number. So that's a rotation of a line. So really what you've done is you've projected the moment, how much of this moment onto that line, just like you project a force, right? So if you had, another way to think about it is if you had, a force in 3D, if I had a force going like that, then I could project that force down the x-axis. And all I'm doing is I'm saying how much of this force here is going down the x-axis. And to do that, I would just say that force dot product with I, and I just get that. And so, and you get a scalar value. So you're just saying that out of whatever force in this direction, how much is going down that axis or any line whatsoever. It really doesn't matter. And we know that whether you reverse them or not, it's, this is associative, so it doesn't matter. Anyway, so that's just about out of time, but that's what chapter 3 is. That's the introduction to it. So I encourage you to look at the lectures. If stuff's not totally clear, please come to office hours. I can explain in more detail. Sorry, we're out of time. I have something else at 3 I got to get to, but I will have the quiz on Wednesday. I'll put up some information about it, but plan on taking the quiz between 2, 10, and 3 o'clock on Wednesday. All right. Any final questions before we go? All right, you guys. Well, thanks for coming. I hope that wasn't too much of a blitzkrieg of information, but again, we'll talk soon, and have a good week. Take care.
Thank you.
Thanks, Prof.
Thank you, guys.